So okay, in this video we are going to see an example on computing the total current. For this example, we have a bunch of three loads. These trees are power load, of course. The three power loads are connected to the voltage source with the voltage of 480 V RMS. What do I mean by power load is that the quantities of the loads are given in terms of the power quantities. For example, here we have the three loads sharing the same, having the same voltage drop across each of these branches. So we have the three loads. For the load 1, it indicates that it absorbs 12 kilowatt and 6.667 kVAR. So in this case, you have to know that this the unit, right, 12 kilowatt is a unit of active power, and the kVAR is the unit of reactive power. Okay, so the first load is consuming both active and reactive power. For the second load, which is here, this is the first load and this is the second load. The second load is is absorbing 4 kVA. So the kVA here is the unit of complex power, right? This is an S. Okay, remember S is equal to P plus JQ. Okay, and the S here is sharing the unit of VA. This is the standard unit, and the P is watt, and the Q is VAR. Okay, and if you have 1,000 of the basics, so you have multiplied by kilo. Okay, kilo, or if you have a million times greater than the base unit, you would have MVA, megawatt, and VAR. So VAR here would stands for voltage, volt amp reactive. Okay, so now you can see that the load 2 absorbs 4 kVA and the power factor of 0.96 PF leading. So what do we know by the leading, the specification of leading? So for leading power factor, you have to remember that the leading power factor is a capacitor. Okay, it's a characteristic of a capacitor. So leading power factor would mean that the reactive power is negative. Okay, leading power, if you draw the phasor, it would be like this. The V is here, the I is here. Okay, and the complex conjugate of I would be at this position. Is right the same magnitude with the different with the negative angle. Okay, V times I conjugate, your power triangle would be like this. This is P and this is Q, right? So the Q would become negative. Okay, so in this case, this is clear. Okay, so it actually, the load 2 just consume P and contribute Q, right? So the load 3 is the unity power factor. Unity power factor, you would know that there is no reactive component, so there is just 15 kilowatt. Okay, the problem asks you to compute the total current, I total, meaning that from this picture you can see that if you want to compute the I total, which means that the total current that is drawn from the source. Okay, in this case, of course, the problem can also ask you to determine the current that is consumed by the first load, which is I1 here. The problem can ask you to compute I2 and I3 as well. Okay, but for this particular problem, we just stick to determination of just the I total. Okay, so this kind of problem, okay, you can use the technique called power triangle, which we discussed in the lecture. Okay, in the technique of power triangle, you need to write the loads, right? Load 1, load 2, load 3, we draw a power triangle for each of the loads, and we just sum the active component, which is P, and the reactive component, which is Q. We just sum all the P's and all the Q's, and we try to determine the resultant or the total power triangle for the whole load. Okay, once we know the resultant power triangle, you can, if the problem asks you to find the I total, you know that we are trying to lump. The technique of power triangle is that we're trying to lump this all these three loads to be one big single load. Okay, we are trying to find how much the equivalent load of these three is. Okay, in this case, if you use the power triangle technique, meaning that you want to find the equivalence of the load from each of these power loads. Power loads in this case, what I mean by power load, meaning that the load that gives the specification in terms of power. Okay, but in this problem, okay, the problem also asks you to determine the equivalent impedance. So this power load, okay, we want to express how much, what is the equivalent amount of the impedance corresponding to this power load. Okay, everybody knows that when we express the circuit element, right? The circuit element that we use when we learn the circuit. Okay, normally we would try to express this in terms of impedance if it is in the AC circuit, or if it is just an DC circuit, you express in terms of one parameter called R. Okay, but in this case, if it is an AC, you normally express in terms of impedance, which is, in this case, this is R plus Jx, consisting of both active or real part and imaginary part. Okay, so the problem here, we want to find the equivalence of the impedance, which is how much of the C here is when we apply the same voltage as the given here, which is 480 volts RMS, and that would produce the same power as the total of these three loads. Okay, what is the C here? Okay, what is the C total? Okay, that is the second question of this problem. Okay, this is the second question of this problem, equivalent impedance. So before I give you the solution, why don't you pause this video and try to work on your own pace, and we will check the solution and the answers together. So please pause the video and we come back later. All right, I hope you could do it. Okay, I will try to show you the solution. I will start by the power triangle technique. Okay, the power triangle technique, you have to remember, right? You should remember the way we draw the power triangle for each type of the load. So the first load is that the first load absorbs both P and Q. So absorption means that the power quantities are both positive. Okay, so in this case, let me use the green for the power triangle. So you see that the first load would become like this, which is the P, which is real part of this. This is 12 kilowatt, and the Q. Okay, this is the consumption, so the Q has to be 6.667 kVAR. Okay, this is the first load. For the second load, it absorbs leading power factor. So the key is with the leading. Okay, well, for you can see that for the leading power factor means that the power triangle would look like this one. Okay, because the Q has to be negative. Okay, and P is always positive because P is the component in which we consume or we use the electrical work. Okay, the P or active part or real part is always positive. So the Q part or imaginary part If it is positive, means that it consumes, or it is an inductor, right? To consume the reactive power. Whereas the leading power factor would means that this is a capacitive element, or it produces reactive power. Okay, so the load 2, which is load 2 is here, it absorbs 4 kVA. So the kVA here is the S, which is here, 4 kVA, and the 0.96 pf leading. So that means that the power angle here would be negative of arc cosine 0.96. So you remember that 0.96 here means that the ratio between P and S, right? Or you can simply straight away, you could write the P, you can decompose this active component or real component of this. You know that 0.96 or power factor is defined by P, the ratio between P over S, okay? Which is a part of, this is the how much ratio or how much portion of the power that would produce the essential electrical work. So you can see that if it is PF is 0.96, so P here would be 0.96 times 4. Okay, everybody knows that 0.96 times 0.96 times 4 would be in this case that would be 3.8398 kilowatt. Okay, and the Q here, you have to decompose this in terms of active and reactive component, as we discussed earlier, or real or imaginary component, if you want to say in terms of mathematics. So we can, if it is in mathematics, we say real part and imaginary part, real part and imaginary part, right? Because this is the axis, okay, real axis, and this is imaginary axis. But in terms of power quantity, we normally would say that this is active component and reactive component, because active means that it produces electrical work. Okay, for active component here it is this much, right? So in calculation for the reactive part, you could also, you can also use the Pythagoras theorem. The Q could be computed from either from this way. Okay, you can do just one of this calculation. Okay, it could be divided. It could be found from square of 4 minus 3.8398 square. Okay, or you could also, you can use the trigonometry ratio, because you see that this is Q over P, which is, what is the Q ratio between Q over P? Okay, this is the 10, right? This is the 10 of the angle here, which is, what is that angle here? If you hit your calculator, that would be 16.26 degree. So Q over P is 10 of this angle, so the Q itself is P10. Okay, Q here is P10. Okay, so now the P here would be 3.83. Or you can do it in this way, because you could find from Q. Okay, Q over 4. Okay, what is Q over 4? Q over 4 is the sine, right? Q over 4 is the sine of this angle, minus 16.26. Okay, then Q is 4 times sine of this guy. Okay, sine of 16.26 degree. So now you can see that sine of negative is the negative value of the sine. Okay, it's negative value of the sine. So in this case you get minus 1.12. The unit is kVAR. So you see that if you put 1,000 times, you also get the reactive component of 1,000 times. Okay. For this is for the load 2. So remember what the steps that we take is that we need to decompose this into in terms of active component and reactive component, and you do this for all the loads that you have in the problem. Okay. So the problem the load number 3 is a unity power factor. So for the unity there is no reactive component. So you have just one arrow of 15 kilowatt, right? In this case, so this 3 triangles, so actually 2 triangles and 1 arrow. Okay, that would represent the different 3 different complex quantities. So by adding, right, by summing all these 3 quantities, because these are the 3 loads, so the 3 loads just consume, right, when we analyze a circuit, you remember the power doesn't have any parallel or series connection. No matter how you connect the element, the circuit element, the power consumption is the sum for individual consumption. Okay, so the power consumption is always an algebraic sum of all of the power consumption by each of every circuit elements. Okay, now you just sum all the power, right? So you sum all the power, you can see that the active part, okay, which is P, I will draw this to sum 1, 2, 3, you sum all these 3, you get the result, which is here. Okay, you get the result here. Now you see the power P is here. P is 12 plus 3.8398 and plus 15. So the you need to check this one more time, right? You please check this again one more time, whether it's correct or not. All right, that should be 30.8938. I think, yeah. Let me see. This is not right. Well, this is a different one. So because the decimal is different, so this is 30.8938. So this is the let me check this again for straight away, because if otherwise you will get the wrong answer. Okay, that would be, this one would be correct, because I need to I have rechecked it already for you, because that would be, the decimal would be 30.8398. Okay, the sum of all this is this one here. The unit is kilowatt, and the sum of reactive component would be, okay, 5.547 kVAR. Okay, the 5 this one, and the resultant S is the sum, the square of this guy plus the square of this guy, and you take the root. That would be 31.3878 kVA. Okay, and this is the total complex power for these 3 bunch of load. So remember, so this power triangle would be the equivalence power consumption of this big chunk of the load. So the 3 load could be represented by a single power triangle which is written in the yellow, in this blue color down here, down there. Okay, with this blue triangle right here. Okay. Now the problem asks you to determine the total current, so you know that everybody knows that S is equal to V times I conjugate. All these are in complex quantity, so we want to find the I total. So you need to put you need to divide V, the complex phasor of V on the both sides, and you take another conjugate to get this the original value back. So it would be S total. I put the total because this is called S total, because total of the three loads and divided by the V, and all together you put the conjugate. Okay, so please don't forget the conjugate, otherwise you would get the wrong answer, because you see from here your total reactive part is positive reactive part. That would mean that this is a lagging power factor. So when you see this is the lagging power factor, means that the V is lagging, V lags the I. So this is V and this is I. So you have to see that your I, the angle of, if you put the angle of V as a reference, this is a reference, so the angle of theta I must be negative, right? Otherwise you don't get the lagging power factor. Okay, now you have to get the negative phase angle of I. So if you forget this complex conjugate at this position, you will get the wrong answer. You will get the opposite phase angle, right? So now in this case, okay, you need to compute this a little bit. You have to you can put this in two forms. Either you could put as a rectangular form or Cartesian coordinate. You put this 30.8398 minus, right, J 5.547 divided by 480, but remember the S here is in kilowatt, okay, but the volt here is 480 volts. So I will just do in the polar form, okay, because you want to get the answer, you want to get the phase angle of the current as an answer. Okay, so I better put this as a polar form, which is in 31.3878. okay, this is the S in terms of the unit of which is kVA. I put the kVA to remind myself that this is 1,000 times greater. Okay, this is 1,000 times greater than the basic unit, and you need to cancel this kilo, right? So the denominator must be in kilo as well. The voltage is 480 volts, which is equal to 0.480 kilovolts. Okay, kilovolts. Now the V here is put as a reference, so the angle here is 0. Okay, and the angle of the upper part, that would be in this case, right, this is the angle of this guy. The angle here, it's, if you keep the calculator, that is the 10.179 degree. So you put this as a 179 degree, and you have to take the conjugate. So once we have the conjugate, this becomes the negative of 10.179 degree, right? So this is the important part. You don't forget, right? You should not forget this kilo. Okay, and the other one is that since there is a complex conjugate over here, so please do not forget this a negative sign over here. You have to put the conjugate, right? So now you just do the calculation in this case. Okay, that would be 7.3404, and the angle of minus 10.179 degree, and the unit of this, oh sorry, this is not the right one. So I put the wrong answer for you. This is 55 point, that should be 55.3912, and the angle of minus 10.179 degree. This is M. Okay, this is the first answer. So the total impedance would be, you know, you have to determine the Z, right? What is the total? The second question is the total impedance, Z. So the Z here, you have to play around with this formula a little bit. You have to change this formula a little bit, okay, which is done in purple here. Okay, I will derive for the Z for you. So now you know the voltage drop across the loads, and we want to find, as I said earlier, we want to find the C, the equivalent C. This is EEQ, that would produce, you know, the same amount of complex power when we put the 480 volts, right? 480 volts RMS, and this when you put this 480 volts across this ZEQ, that would produce the same amount of power as this guy here. Okay, the total S power is the same as this. So as you can see from here, you know the voltage and you know the power, right, which is over here, and you want to know the Z. So we have to transform this the current from this equation. So the S here would be V, I would becomes, because you know this is the Ohm's law, right? V is equal to I times Z. So the Z, the I here is V divided by Z. So please note that when I put the capital letter with the underscore below, that would means the complex power, or this is a polar quantity, and this is the conjugate. Okay, so you know that the conjugate can be distributed, you know, to numerator and denominator, right? So V times V conjugate, this is the magnitude of V squared divided by the C conjugate. So we want to determine the C. So the C conjugate, or C conjugate, would be V squared divided by S, or you take the conjugate on both sides of the equation. The conjugation doesn't play any effect to the square of magnitude, because here V squared would become a scalar value, right? This is a scalar. So the C would become V squared divided by S conjugate, right? This is the equation. So the Z total that you have to answer for this is, or the CEQ. Your CEQ would be V square, which is 480 volts square. Okay, this is in volts square. Okay, divided by S here. So the S you put in terms of, you know, complex power, conjugate of the S. Okay, so the S total here would be this guy, right? 30.83 plus, right, J times 5.547, but you have to take the conjugate of this. So you have to put, in this case you could put 30.8398 minus J, right, 5.547. Okay, this is the unit of this guy is kVA. But the unit of this is in volts, so you have to multiply this by 10 to the third, right, to change this to VA, right? This is the basic unit. Okay, and right, this is you put the conjugation already. So the C here would be 7.2249 plus J times 1.2972 ohms. Or this, if you write this in terms of polar coordinate, this would be 7.3404 and the angle of 10.179 degree, and this is in ohms. Okay, The way you should check your result is that when you multiply this Z by the total current, okay, you multiply this equation A and this equation B. You can do this one yourself. You know that the Ohm's law must be correct, right? It must hold for this case. So if you multiply I total with the CEQ, you should get the V, which is what here? This is 480 volts, right? 480 volts without any phase angle. So you can see that if you multiply the A and B, the equation A and B, you get 480. This would conclude that your calculation of these two questions are correct. So we will see you in the next video clip, and thanks for watching.